Okay, thanks. Thanks, Ken. Let me just begin with a quick recap of what we had last time. The simple pictorial view is that electrons capture an even number of flux quanta to become composite fermions. And composite fermions, unlike electrons, can be treated as non-interacting to the first approximation, except that we have to remember they see only the residual magnetic field, which I call BCF. Then the second thing was to write wave functions based on this idea. So we write wave functions for non-interacting fermions at the effective magnetic field BCF or effective filling factor. We then multiply by this Jasto factor, which does the job of attaching an even number of vortices, or which we often think of as flux quanta, followed by projection into the lowest lambda level. So this is called composite fermionization, and that's something I'll use later on. So you start with something, you multiply by the Jasto factor, followed by projection. That's composite fermionization. So we saw that the theory within this simple model, within this idealized model, I should not say simple, idealized model, where all electrons live only in the lowest lambda level, the theory was shown to work extremely well. So these are some comparisons. So this is filling factor 3.7. In fact, we can show that you can fill higher and higher energy states if you want, by considering higher and higher energy excitations of composite fermions. And it works for 1/3, 2/5, etc. in between. Okay, so the theory provides an excellent account of the phenomenology without any calculations. The computer studies also tell us that the theory is extremely accurate as well, at least for this idealized limit. Now, you would think now we can go ahead and compare with experiments, except that there are some things which have been set to 0 in this idealized model, which plays some role in experiments. And these are, one is finite width. So we set the width equal to 0 in the earlier calculation, and there is lambda level mixing and disorder. So disorder is the hardest thing to take into account, so I will not talk about disorder, but we'll try to now include finite width effects and also lambda level mixing effects. And ironically, we understand the fractional Hall effect part of the physics extremely accurately. It's these other extraneous things which we do not understand as well, which is what makes it a bit harder to compare numbers with experiments. So you might also ask, why bother? We have shown that the theory works, so conceptually we are on very firm footing. But it's one of those things where we say we have a theory, so we'll calculate. It's something where in a strongly correlated system, starting from first principles, there is a hope to make good connection between theory and experiment. So we have spent quite a bit of time on this. So let me just say, okay, so the plan today is this question had come up yesterday, and I would like to just discuss this in a few minutes. So how about the abelian, non-abelian statistic? I will then consider what happens when spin or valley polarization is important. What happens to crystal of composite fermions? How about pairing of composite fermions, which is another mechanism for fractional Hall effect? So yesterday we saw integer quantum Hall effect of composite fermion, which explains almost all the states, but there are some even denominator states which require us to consider pairing of composite fermions. And in the end, I will say a little bit about scaling in fractional Hall effect. Okay, So you may have heard or you may have known that if you assume a gapped state at a fractional filling factor and nothing more, okay, just a gapped state, then you can kind of using very general arguments prove that there must be fractionally charged particles with which obey fractional statistic or anyons. Now, the composite fermion theory gives an account of the fractional Hall effect without saying the word anion. So I did that last time. But one can still ask, what about anions? Okay. So first of all, in case you don't know, anions are defined. Anions are particles which have the property that if you exchange two anions, the system acquires a phase e to the power I pi theta star. So theta star can be for bosons it's 0, fermions it's 1, but it can be some number in between. So that's the definition of anions. And they live only in 2 dimensions because, so this has to do with, so if a particle goes around another particle in a loop and that path has to be distinct from a path where it does not go around the loop, and that can this distinction is valid only in 2 dimensions. In higher dimensions, you can lift one of the paths off the page and continuously merge it into the other path. Okay, so the fractional charge and fractional statistics was considered in early 80s, and as I said, these follow from very general topological arguments. So let's come back to composite fermion theory and ask, how do we understand excitations? So it turns out, and as you can imagine, a quasi-particle in the theory is just one isolated composite fermion in an otherwise empty lambda level. Okay, so this is quasi-particle of 1/3. This is of 2/5, 3/7. They're all composite fermions. In fact, they're the same composite fermions that you have in the ground state. So there is this unified picture. That's very appealing. Quasi-hole is just a missing composite fermion, and again, it's the same for all fractional Hall states. Neutral excitations, which I already talked about earlier, are particle-hole pairs of composite fermion. So, in fact, this actually gives you a quantitative description of the actual quasi-particles and quasi-holes. So I am showing you here. So on every plot here, there are 2 curves. One is exact quasi-particle or quasi-hole density, and the other is that we calculate from these pictures without any other adjustable parameters. And this is a 12-particle system at 1/3. At 2/5, you see this comparison. In fact, you may not be able to see that there are 2 curves. So this actually gives an almost exact description of the actual quasi-particles and quasi-holes that you see in numerical studies. Okay, which are exact. So the description is exact, but then you might say, well, isn't there a paradox? Composite fermions are charged 1 fermions, they're fermions, as the name says. On the other hand, we have been given to believe that quasi-particles have to be fractionally charged anions. So in fact, there is no paradox. It's a question of what is the reference state. So if you take reference state as the state which has no particles at all, then these are charged 1 fermions. But if you take as the reference state the background fractional Hall states and you measure things relative to that, they would be fractionally charged anions. And so it's a question of what measurement is being done. Okay, so let me in fact I would say that composite fermion theory is the simplest way to derive fractional charge and fractional statistics. And let me do that. So what I'm going to do is so let's say I have a fractional Hall state, uniform density. I'm going to add an electron to it. Of course, the electron has charge 1. So overall, if you look at the whole system, I have added charge 1. But what happens is that as the electron gets dressed by vortices to become a composite fermion, the system has to do the following. So first you insert 2 vortices at the points where you are about to put an electron. So one can show that each vortex has a charge deficiency which is precisely equal to the filling factor. So you basically empty one orbital. So this charge moves to the edge. Okay, it goes to the boundary. And then you add electron which has charge -1. So the net charge here comes out to be this factor. Okay, so it's equal to the charge of the electron plus, which is negative, and plus the charge of the vortices, which relative to the fractional Hall state, background fractional Hall state, is a positive number, and 2 together give you this. Of course, there is no mystery here. So, I showed you charge density profiles. So I can just take those and just integrate the charge, and I'll get this. So this, now how about fractional statistics? So we'll do the following experiment. So, earlier I said you take one particle around another, and that gives you a phase which is e to the I theta star. Here there is a problem, which is that there are 2 contributions that are associated with this Berry phase. One is coming because of the statistics of this quasi-particle, but there is another contribution because it's a charged particle in a magnetic field. So there is an Arda-Bohm phase. So I need to subtract that to kind of extract the contribution coming from statistics. So we'll do it in the following way. The Berry phase for a closed loop of a composite fermion, it doesn't matter to, you drag a composite fermion around. The Berry phase has 2 contributions. One is the Arda-Bohm phase coming from the electron. The other is the Berry phase coming because there are these vortices which are going around, and when you take a vortex around an electron, it gives you a phase of 2 pi. Okay, so if you know how many particles are enclosed here, which I call n sub e, then this is the answer. If the density were uniform, I would just replace the number of enclosed particles by density times A. And in fact, this gives me the formula for the effective magnetic field, BCF. But now let's ask, suppose I know the answer here, I insert one more quasi-particle here. What is the change in this Berry phase? That's just, so if I look at this, the first term does not change, remains exactly the same. The second term, I have changed the number of particles inside the loop by a fractional number, by the charge that I had calculated. And therefore, this tells me that the change in the Berry phase is given by this expression. This is precisely what the interference experiments measured, by Mike Manfra or whatever. So one can fully well understand them in terms of composite fermions and fractional charge, but one can also think of it in terms of fractional statistics. So you say one has, it's when one quasi-particle goes around another, there is this contribution. Okay, so you can think of it as fractional statistics. One can measure, in numerical experiments, we can calculate fractional statistics. So this is the statistics parameter for a quasi-particle or quasi-hole going around another at 1/3, and this is at 2/5. And as I said yesterday, up to 10 or 15 magnetic lengths, there is a correction. Beyond that, the statistics converges. So if you want to have well-defined statistics, the quasi-particles have to be sufficiently far from one another. The anion nature is not well-defined all the time. Of course, composite fermions are always well-defined. Okay. So now let me come to finite width and lambda level mixing. So finite width will take into account in this fashion. We'll say, let's say yes, please. Magnetic length. Yeah. So magnetic length itself can be like 20 nanometers or something. So 15, that's fairly substantial. And that's only for 1/3 and 2/5. As you go to higher order fractions, quasi-particles become bigger and bigger. So as soon as they start overlapping, there is some correction to statistics. Okay, so what we are going to do is use a local density approximation to determine the transverse part of the wave function. And once we know that, we'll include that to calculate the effective two-dimensional interaction between electrons. Okay, so I guess the idea here is that if you have strictly two-dimensional system, as two electrons come close to each other, it's like 2 points interacting with one another. But if you have a finite quantum well, it's like 2 disks are coming close to each other. So it kind of depresses the short-range part of the repulsion. That's what finite quantum does. How about lambda level mixing? So the parameter of interest here would be kappa. So this is Coulomb interaction. L is the magnetic length. So Coulomb interaction divided by the cyclotron energy, that's called kappa. If kappa is very small, then lambda level mixing can be neglected. But in general, you have to keep track of this. In fact, for n-doped gallium arsenide systems, typically kappa is small. It's less than 1. I mean, it's not like very small, but it's certainly less than 1. But in hole type systems, you can have kappa to be pretty large. It can go up to 20. And therefore, you would think lambda level mixing can be quite significant. So how do we take that into account? Well, we are going to use a method called fixed phase diffusion Monte Carlo. Now, I'm not going to go into technical details, but just to give you a quick flavor for what it is. Okay. So suppose you knew that the wave function is everywhere real and non-negative. And that's true for the ground states of bosonic systems. So in that case, if you go to imaginary time, the Schrodinger equation becomes a diffusion equation where you think of wave function as the density of the diffusing particles. And then what you have to do is you evolve this in imaginary time, and if you evolve it long enough, it leaves you with the ground state. Okay, and the reason for that is, suppose I knew how to express this in terms of eigenfunctions, then I know that if time goes to infinity, the lowest eigenenergy is the only one that survives. All others fall out. Now, in fractional Hall effect, the wave function is complex. It's certainly not real and non-negative everywhere. So here, a pretty remarkable trick was developed by Gerardo Ortiz. Very clever. They said, well, let's assume some wave function. Let's write it as a modulus times a phase factor. Okay. And then furthermore, let's assume that the phase factor does not change. So that's the origin of the term fixed phase. Then you can incorporate this phase into the Hamiltonian and write an equation, Schrodinger's equation, just for the amplitude part. And the amplitude part, by definition, is real and non-negative. So now we evolve it in imaginary time, and it gives me the lowest energy state within this phase sector. Okay, so if somehow I knew the phase sector, then this would give me the exact ground state. But otherwise, the goodness of the answer depends on how good your choice of the phase is. So how do we determine? I should mention that this produces results which are certainly non-perturbative in this parameter kappa. And okay, so how do we decide what phase choice to make? Well, there was some evidence from early numerical simulations by Cyrus Umaygar and Guklu that the phase of the lowest lambda level ground state is the best choice. So if you knew what is the best state in the lowest lambda levels, you choose the phase of that, and somehow lambda level mixing does not change the phase significantly. But we don't know, but in physics you do what you can do. So we'll just go ahead with this choice and see what we get. Okay. So again, there was a question yesterday, what happens with composite when electrons have several flavors like spins or valid degrees of freedom? So let me come to that. So again, we do exactly the same thing. So we map the problem of electrons at filling factor, let's say 4 nines, to composite fermions at filling factor 4. Okay. And then you say, let's say I have spin degree of freedom. I want to know what are the possible choices for ground state. Well, you can either put all electrons or composite fermions in the same spin. You can have 3 lambda levels occupied with spin up, 1 with spin down, or 2 and 2. Okay, so these are the choices. So for any filling factor, you can just do this, and it gives you what are the possible spin polarizations for the state without doing any more detailed calculations. But now we would like to, if I let's say ignore the interaction between composite fermions, then the only parameter, the only 2 parameters are the cyclotron energy of composite fermions and the Zeeman energy. So you can see that as if I'm at 0 Zeeman energy, this state will be preferred. As I increase Zeeman energy, it will go from 2 2 to 3 1 to 4 0. Okay, and we can do that for any filling factor. So it turns out this works beautifully. And I think perhaps the best data is in graphene by my colleague Junju, whose slide I have taken here. Here it's the valley polarization. Okay, valley degree of freedom, and for valley Zeeman energy, it can go from negative infinity to infinity. So what she finds is that this is composite fermion filling factor. Okay, so actual state maybe 2/5 or something like that. She finds that there is a transition from 2 0 to 1 1 to 0 2 at 3 7s, or this is when composite fermion filling is 3, goes from 3 0 to 2 1 to 1 2 to 0 3. So the number of transitions seen here exactly match with what composite fermion theory predicts. And moreover, by fixing the mass or the cyclotron energy, treating one parameter as an adjustable parameter, you say, okay, the positions of the transitions are given by these circles. There's beautiful agreement between what you get from that one parameter theory and the experiment. Now it turns out that if I say, look, I don't want to do any fitting, I just want to calculate the whole thing, then we find that there is the mass has a disagreement of a factor of 2 or 3, which I will come to in a moment. So which, yeah. Yeah, so here it's only the valid degree of freedom that's active. So spin is not changing in this. Probably. Zeeman energy is large, so spin is fixed. It's not active in this. I mean, you can also generalize this to SU4, when both the value and the spin degrees of freedom are relevant. Okay. So these are some calculations we had done a long time ago. So I begin with a wave function of electrons where some spin up lambda levels and some spin down lambda levels are occupied. The filling factor n is of course equal to the sum of the two. You composite fermionize it in the standard way, calculate the energies, take thermodynamic limits, and it tells you that the ordering you thought would be, the ordering you would think is the correct ordering. So we have not included that is J1 energy. 2,2 has the lowest energy, followed by 3,1 and 4,0. But to, okay, so here I'm showing you all the results. This is not graphene. We don't know how to do fixed phase diffusion Monte Carlo for graphene. This is for gallium arsenide quantum wells. The experimental results are these stars. And with the calculation that I showed you on the previous plot, we would get, so I'm plotting critical Zeeman energy, where transition is seen from a fully polarized state to a non-fully polarized state. The transition would occur here. So you see, there is a disagreement. But once we include finite width and lambda level mixing, the theoretical result goes to these circles, and you can see that there is an extremely good agreement. In fact, the energies of these differently polarized states, they differ by like 1%. And we are able to calculate that 1% difference to within a few percent with the theory. There is, so because the question of particle-hole symmetry came up, there is also a lack of particle-hole symmetry in these experiments. So, for example, a lot of experiments have seen spin physics in the vicinity of 3 halves. Okay, so 3 halves in gallium arsenide is in the 0, there is 0 up and 0 down, so up to filling factor 2, only the lowest lambda level is occupied. But you expect particle-hole symmetry to relate the physics in the vicinity of 3 halves to physics in the vicinity of 1 half. But people saw a lot of spin physics near 3 halves, but not near 1 half. So that had been a puzzle. So, for example, Jim Eisenstein was telling me he was the first to see a spin transition at filling factor 8/5. And he said he went to 2/5. And he said, okay, I went to the same magnetic field, so he reduced the density, just was not able to see it. So the transition at 2/5 was seen much later by Wu and Kang. So he had to apply pressure to reduce the Zeeman energy of the system, and then he could see it. So let's see if we can understand that. So so this calculation is a bit time consuming. So we just looked at 2/3 versus 4/3. And indeed, we find that at 4/3, the critical Zeeman energy goes up, and at 2/3, it goes down. Okay, so that's why the spin physics is harder to say in the vicinity of 1 half. Okay, let me come to the next topic, which is crystals of composite fermion. So one of the interesting aspects of fractional Hall effect is that this is 1/5, this is 2/9, and there is an insulating state here in between the two. You see very beautiful 1/5, beautiful 2/9. So in the past, people saw such insulating states, but as they improve the sample quality, they go away. Okay, but this one, they have improved the sample quality by a lot, by a factor of 100 maybe since the first observation. Still, this stays, and therefore it's very likely a finned Wigner crystal. Okay, so this you would think. Also, these are strongly correlated states. So you would think that, just nearby state perhaps also is strongly correlated. So this, so the picture is that it's a finned Wigner crystal, although nobody has actually seen and imaged the electrons here. So how do you make a crystal? Well, you can create a localized orbit localized electron and put the electrons in in a triangular lattice and anti-symmetrize the wave function. That is a Hartree-Fock wave function for a crystal. But we considered the possibility that the crystal could be a crystal of composite fermion. So what we do here is that we do not bind all the vortices that are available to the electron. We bind a few of them, and the remaining degrees of freedom are used to make a crystal. Okay? And how many vortices are bound is a variational question. Whatever gets the lowest energy, you bind that many vortices. And the reason why composite fermion crystal may have lower energy is because of this Jastrow factor, which keeps electrons away from each other. The fluctuations on neighboring lattice sites, they are correlated. Okay, so earlier they could move like this. So that gives rise to large energy, but now they are moving in a correlated fashion, and that's why it can give lower energy. So so what I will show you are some, variational calculations looking at the competition between the crystal and the liquid state. We like the spherical geometry for many reasons. So now you cannot put a crystal neatly on a sphere. So what we do is we consider what was called a Thomson crystal. So Lord Thomson, long time ago, was trying to make a model for atoms. And he asked the question, okay, if electrons are sitting in a spherical shell, that was his model. So one can assume that electrons are just classical charged particles and figure out what positions would give the lowest energy. And that's called a Thomson crystal. So it's basically a triangular Wigner crystal with some defects. Okay, but the contribution of the defects goes to zero as we go to larger and larger systems. So there are two types of crystals. I can make a crystal of all composite fermions like this. So we call this type 1 crystal. So this has the property that if you pin it, you get an insulator. But there's another crystal. So suppose I start from 1/3 and start putting, start moving away from that filling factor. Let's say I start filling the second lambda level. Only the composite fermions in the second lambda level can also form a crystal. So that's like this. If you pin this crystal, you get perfect fractional follicle. Okay, because we know that if all the quasi-particles or quasi-holes are localized, that gives quantum Hall effect. So we call this type 2, in analogy to type 2 superconductors, where if you have vortices and if they are pinned, you get perfect superconductivity. Okay, so a student of mine, Alex Archer, he looked at the problem and he found, so here this green is the energy of crystal of composite fermions with two vortices bound. Okay, black is the energy of this electron crystal. So you can see that there is a reentrant transition here. So this is 1/5, 2/5. So there are these cusps. So we can actually see this cuspy structure of the energy of the liquid, and the energy of the solid remains flat. Continuous. There is no cusp, and you can see that there is a fractional Hall state at 1/5 at 2 lines, but in between you get a crystal state. Okay, here. So this actually captures this reentrant transition between 1/5 and 2 lines. But the crystal in between is not just an electron crystal; it's a crystal of composite fermion. In fact, it was believed that if you go to very low fillings, you get a crystal. But we believe that it's not just a monolith, or it's not a single crystal state. There are transitions from crystals where composite fermions bind 4 flux quanta to 6 and so on. Okay. Was there a question? Yeah.
The first round like earlier people that added correlate on top of parties bar. Are you different in that or?
I don't know. It'll be good to test. Okay, I think that will be a very good home assignment problem, as Sean would say. Okay.
Like, the same solving, I think that is in voice, so tell me that.
Okay, I have to say that I think this crystal has some topology in it, because we have found, there are vortices bound to electrons. If this was a liquid state, then you can take this, move around and kind of study the topology. But in the crystal state, we don't know how to test this. So at this moment, at least what we know is theoretically they give very different energies, but experimentally I don't have a sharp way of distinguishing between them. So for example, the localization of the particle at the lattice site, it depends on how many vortices are bound. But that's to find a parameter for an experiment to ever observe in a decisive fashion.
So you think is there a possibility that comes with to find an odd number of them, so if they become boson, the boson can orbit this star, okay?
Yeah, that's we haven't tested that possibly. So you're saying that you take mega crystalline bosons, and that's also a good idea.
The odd,
Right.
there's the order following that the factor then localize and then.
Yeah, that's also a very good idea. Yes, sir.
This type populate get target. Or
You could say, yeah, they're like, yeah. I guess at some level they're the same.
let's just have I think the
Electron and
or
you can make either so depending on what filling factor you're at. So let's say you're at 3/5. You can think of that as 2/5 of holes, and you can then make a composite fermion, which is bound state of a hole and some vortices, and so you can or let's say start from 2/5 and you go in one direction or the other direction. In one direction you get a crystal of quasi-particles, in the other direction you get quasi-holes. Maybe that's what we meant.
Yeah, and not like how you by the are they other time we see playing out everything to get like those like cats like they.
I don't know. I mean, it's possible that if you include some correlation effects on top of this. So this is the Hartree-Fock crystal without any other correlations added to it. It's possible that energy might come down, but at least, so we don't know it. That has not been done. Okay, so lambda level mixing. Yes, sir. Yeah.
Wait till you like here. And I
Okay, so the thing is that on torus, people knew how to write wave function for the Laughlin state and quasi-hole of the Laughlin state, and nothing else. So it's only relatively recently, maybe 5 years ago or so, that a student of mine, Songyang Pu, he figured out how to construct wave functions of all fractional Hall states on torus. But these calculations were done earlier. So we wanted to look at many different fractional Hall states. And so now it's possible to think about doing the calculation on torus because you can compare energetics, in the same geometry and system. Okay, so another interesting thing is the following. So, this behavior is seen near filling factor 1/5, But if you go to hole type systems in gallium arsenide, you see this is 1/3 and 2/5. So it just looks like what, so this is not there in electron type system, except that the parameter kappa is big here. It's like 7. So you can actually in hole type systems go from kappa equals 7, and by the time we get to 4, that insulating state has disappeared. So, this peak might look the same, but this, the axis here, the units have changed quite a bit. Here you can see all of this other structure. Here you don't see any of this stuff. So it's clear that lambda level mixing can induce a crystal. Okay, so we unleashed our fixed phase diffusion Monte Carlo onto this problem, and we came up with this phase diagram. So for in the vicinity of 1/3 and 2/5, you see a crystal if kappa is above 6 or 7, something like that. In the vicinity of 1/5 and 2/9, the picture looks like this. So even with 0 lambda level mixing, there is some region, but the region expands as you increase the lambda level. And surprisingly, the structure is kind of like these pointy hills. So Mansoor Shagan, he looked at this experimentally. Although it agrees so well with theory that could as well have been theoretically. So for example, here these are our theoretical lines. The solid symbols are crystal, and this empty symbol is a liquid. So he's a transition at exactly where we predict. Here he sees it's a liquid all the way. So this. We were kind of surprised by how good the agreement was. He also looked in the vicinity of 1/5 and 2/9. So here he also did finite width dependence, and he found in our paper in some supplemental place we had also given results for finite width, and it seems that they all agreed. So if you somehow include the width carefully, the experimental results and our theory, they seem to agree extremely well. So one question was, why does the fixed phase diffusion Monte Carlo work so well? So I showed you earlier results for spin phase transitions. These are results for competition between fractional Hall states and crystals. We don't know why it works so well, but there's another evidence in favor of this. So this is a student of mine who did this work. So he is a super student. So he applied this neural network. So one is coming at the problem from a completely different direction. And what he found that all the energies that we had calculated using fixed phase diffusion Monte Carlo, he calculated using this neural network, and he says he cannot find the difference. So at least it gives one other data point that says that this may not be a completely crazy thing, the fixed phase diffusion Monte Carlo. Okay, now there is also this puzzle at very low filling factors. So let me show you results here. So this has been known since 2002. The experimental observation is the following. If you go to very low temperatures, then the resistance just goes to infinity. At some point, it cannot be measured. So you increase temperature and you pull the resistance down into the region where it may be measured. Once you get there, you find that there are these minima, which very nicely correlates with fractions that we expect in fractional Hall. So, in fact, the minima are seen in the vicinity of 1/7 to 1/9. Here, these are some recent results. You see, these are from Shagan's group. 17, 213, 319, precisely the fraction that you expect. And as you change the temperature, the minima stay wherever they are. Of course, if you go to low temperatures, again, this will shoot up to infinity. So what's happening here? If at zero temperature it's an insulator, how come there are these minima that correlate with fractional Hall effect? So that was the puzzle. So because of earlier results, and in fact also the result that I showed you by Alex Archer and results by Steve Gerwin and so on, we have kind of come to believe, or we have convinced ourselves that below 1/5 it's all crystal. Okay. But if it's all crystal, how can we understand this? So we looked at this problem again. So all the earlier results were kind of based on some variational comparisons, but that depends very sensitively on how good your variational approximation is. If you make one better, things should change. So we looked at this just by exact diagonalization, and this is 1/5, 1/7, 1/9, 1/11, and there are some other fractions also, 2 over something also done here in this same paper. And these systems are not particularly small. They go up to 10 or at least 8 particles. And within this, so if I did not know about crystal, I would have no reason to suspect that there is a crystal. It looks just like a fractional Hall state. One can calculate the gaps. So this is the gap of the to creating a quasi-particle and a quasi-hole. It seems to converge to a finite value to the extent one can surmise from these studies in the thermodynamic limit. So therefore, I think it's very, very possible that that precisely at these fractions, 1/9 to 17th or whatever, it's actually a fractional Hall state. So the picture that I have, that I believe is true, is that the energetic or the system looks like this precisely at these filling factors, 1/7, 2/30, 3/19, etc. There's a region where it's a fractional Hall state. In between, it's a crystal. Okay, so now as you increase disorder, disorder favors crystal, because crystal can better adjust to take advantage of the disorder. The liquid, incompressible liquid, is kind of flat, so it cannot do too much in the presence of disorder. So perhaps the phase diagram looks like this. Now, as you raise disorder, so let's say if I was sitting at 1/7, okay, at 1/7, if there was extremely weak disorder, I would see perfect fractional Hall effect, no problem. But as I increase disorder, so long as the quantum Hall effect, so when I increase disorder, let's say it changes the local filling factor, okay? So then I have regions of fractional Hall state and regions of crystal. If fractional Hall state percolates, then in principle I'll see fractional quantum Hall effect. But at some point, it's the crystal that percolates, and then it becomes insulating. But nonetheless, this is a crystal with big puddles of fractional Hall effect, and they would depress the resistance when we go to finite temperature. So at finite temperatures, this has less resistance than a system that's fully crystalline, because here a particle can jump here and then zoom, no resistance all the way to this point, then jump here, so it can, the current can flow more easily because of the presence of these puddles of fractional Hall state. So the prediction here would be that eventually, if the samples could be made cleaner and cleaner, there should be fractional Hall effect at all of these. But at this moment, you see this behavior that experiments show, just because it's the crystal that's percolating, but it has puddles of fractional Hall effect. Okay, let me just mention, we have not looked at this problem recently at all. So don't ask me any questions. But long time ago, Vito Scarola had looked at the problem. So just like electrons have bubble crystals and stripes, he asked the question, can composite fermions also have that? So he found that in the second lambda level, so this is nu equals 1 lambda level, there is in the vicinity of half filling of composite fermions, there would be stripes, second lambda level and above, and in these regions, there could be bubble crystals. And recently, there have been 2 papers very recently, so that's stripe phase. So this is happening at 5/8, which is exactly halfway between one nu star equal to 1 and nu star equals 2. So it's, in terms of composite fermion. So there is this big anisotropy depending on whether you're flowing current in this direction, that direction, which is, and there has been a reentrant transition seen at 3/5, okay, and or 5/3. So that is interpreted in terms of this bubble. Now, how much time do I have?
Yeah. About 10 minutes on cue. Yeah. But
Okay.
deciding whether to want to say some kind of lecture or stay or go. I think that
And let me talk about the superconductivity. I can probably finish that in 10 minutes and we can have questions later on. Okay, so if composite fermions were completely non-interacting, they would show those sequences of fractions, and at even denominators we would have Fermi-Cs of composite fermions. But it turns out that many even denominator fractions have been observed. So it started with 5/2 long time ago, but now 1/2, 1/4, etc. have been seen in wide quantum wells. So there is evidence for many even denominator fractions. And the picture is that here, for some reason, there is pairing which opens a gap to produce spectral hologram. Now, you might ask, so this kind of connects to the previous talk by Andre. I mean, you might ask, how can we have pairing if we have only repulsive interaction? That's like something we would, that's the fundamental question of high temperature superconductivity. How can you have pairing with such strong repulsive interaction? The thing is that it's not pairing of electrons, it's pairing of composite. So the interaction between electrons is strongly repulsive. We know that the interaction between composite fermions is not the same as that between electrons, it's different. We know it's much weaker than the interaction between electrons, and there's nothing that says that it cannot be weakly attractive. Now, empirically, what we have found is the following. So if you take a system where the short-range interaction is very strong, then you don't see any pairing. Okay, short-range interaction between electrons is very strong. You don't see pairing. But if you reduce the short-range repulsion, strength of the short-range repulsion, at some point, the interaction between composite fermions becomes attractive and you see pairing. So there are 3 ways one can do this. One can either go to a different lambda level, because we know as you go to higher lambda levels, the interaction is not as strongly repulsive at short distances. We can increase the quantum well width, as I just mentioned earlier. That makes the short range part less repulsive, or we can switch on lambda level mixing, because that also screens the short range part of the interaction. Lambda level mixing would screen whatever is the strongest part of the interaction, and if that's a short range part, it will screen that. Okay, so in fact, all 3 have been seen. So let me show you how. Also, let me say there are some previous approaches. So there is, of course, the Pfaffian and anti-Pfaffian wave functions of Bohr and Reed. I had constructed some wave functions which go by the name Parton wave functions, and it turns out many of them describe paired states. Then there are wave, so there has been quite a bit of study of these wave functions. I find one thing unsatisfactory about those wave functions, which is that they are not variational wave functions, so we don't know how to improve upon them. And unlike the BCS theory, I do not see Fermi-C. If I look at Bohr-Reed, I say, what's the connection with Fermi-C? Okay, for all of these wave functions, that's a problem. So I would like to have something which is kind of mimicking the BCS theory to the closest extent possible. So we have done that recently, and again, coming back to an answer that I had given earlier, you could ask why this was not done a long time ago. And the reason it was not done a long time ago is because we didn't know how to work with torus geometry. We didn't know how to write these wave functions in the torus geometry, but now we have done that. So all of these calculations I'm going to show you could only be done now. So the idea is very simple. We know what the BCS wave function looks for electrons. I'm going to composite-fermionize it. So I'm going to take so here the electrons have all same spin. I mean, you can also consider spin singlet superconductivity, but I won't talk about it now. So electrons all have the same spin, so spin is not a parameter here. In that case, it's known that this BCS wave function has this form. So you take particles 1 and 2, put them in some state, and you put all other particles, all other pairs in the same state, anti-symmetrize at the end. That's the BCS wave function in real space. So now we have to have some form for this. So I'm going to, following BCS theory closely, write it in this fashion. Delta is the gap. L is the angular momentum of the pair as defined here, e to the power minus I L theta. If L is equal to 1, I'll call it T wave. If L is equal to 3, I'm going to call it F wave, superconductivity. And we are going to do one more. So that's one parameter. We are going to introduce one more parameter, which is we'll put a cutoff on the integral of K. So you might naively think of it as the, like a Debye cutoff that we have in standard BCS theory. So there are two variational parameters. We are going to minimize the energy with respect to that, with respect to these parameters. This wave function reduces to just Fermi-C when either you put gap equal to 0 or cutoff equal to K. If the lowest energy is given by this, then we have Fermi-C. Otherwise, we have. Okay. So, in the interest of time, let me skip over these and just show you the results. So let's first work at filling factor 5 halves. Okay, so this is 1/2 in the second lambda level, and what we have done in this and some other plots that I'm going to show you, we change delta. For each delta we try to find the cutoff wave vector which gives the lowest energy, and that's what I'm plotting here. So you notice that Fermi-C energy is here, but for some finite value of delta, we can reduce the energy. And it turns out the P wave gives the best energy. So it shows that there is a P wave instability. Just for comparison, if we do the same calculation at filling factor 1/2, lowest lambda level, we do not find any instability. Okay, so let's come to something new. So Mansoor Shagan had seen the following. So here he is plotting the resistance as a function of the density. As you increase the density, there is no quantum Hall effect at filling factor 1/2, but now suddenly you see some fractional Hall effect here. So in the density width plot, the state below or the left side of this curve is compressible. As soon as you cross this line, it becomes incompressible. There's another transition. I will not talk about that here. Okay, so we, Anirban Sharma is the one who did these calculations. He said, okay, let me change the density and ask what state has the lowest energy. He found that it remains Fermi up to some point, and then it goes into a P-wave field. Okay? Or you could stay at a fixed quantum well width, change the density, and again you find that at some point it goes, there is a P-wave instability. Let me also mention that if we take more Reed wave function, then it never is stabilized. It always has higher energy than the Fermi. The gain in energy is extremely small, so it's a rather subtle effect here. Okay, so Anirban did the calculation for number of well widths and densities. Wherever he found a Fermi, he put a blue symbol. Wherever he found a P-wave paired state, he put this red square, and this is the experimental line. So it's remarkably good agreement between theory and experiment. They match beautifully. A similar thing happens at filling factor 1/4. And again, Anirban did the calculation. This is the theoretical phase boundary. This is where the experiments, so there are 2 data points for experiments. The agreement is not as good, but it's extremely good. We sometimes get spoiled by the quality of agreement, but this is really good agreement here as well. Then a student of mine, Tongju Zhao, he asked, okay, can we induce pairing by, so I have already talked about 2 mechanisms, going to higher lambda level or increasing the width. He asked the question, well, can I induce pairing by enhancing lambda level mixing? So he took many different types of states for each. So that's the starting state using which we fix the phase. And using each one of them, he applied fixed phase diffusion Monte Carlo, estimated the thermodynamic energies, and he found that at filling factor 1/4, you have a Fermi up to this point, and then it goes into another state, which is paired state with n equals -3 momentum, pair momentum. And indeed, very soon, such evidence for such a state was seen. So this is in whole type samples. Kappa is around 3 to 6. So we actually had predicted kappa, which was higher, but at least there is evidence for one. Okay, so we are happy. Some more work would have to be done to completely convince ourselves that this works. Okay, so a number of states have been studied, and here I just list the angular momentum of the pairs, and also mention that the angular momentum of the pair can, in principle, be measured in thermal Hall experiments because it's related to what is known as the central charge. Okay, so maybe I'll just show this slide and call it off, okay? So, in condensed matter physics, we like the idea of emergence. Okay, we like the idea that you start with something, but the way to describe the system is in terms of some emergent structure, some new objects emerge. In fractional Hall effect, actually, you can have emergences on top of emergences. So I'll just give an example. So let's consider fractional Hall or system at filling factor 3/8. Now, you say, okay, I'll bind 2 vortices to each electron to convert it into a composite fermion, and the filling factor for this becomes 1 plus half. So I fill the lowest lambda level, filling factor half here. But now these can bind 2 more flux quanta to become composite fermions carrying 4 flux quanta, and they see 0 magnetic field. But this is not the end. This would give Fermi, but they actually pair to form an anti. I mean, the prediction is they form an anti-Pfaffian state, and this is what is responsible for fractional Hall effect at create. So it's spectacular, I would say. And I think I won't have time to go into this, so I'll just stop here and thank you for your attention.